All right. So, hello everyone, and welcome once again to Makeland 360. Um, Good to see you all again. Okay. So, if you have joined, kindly type hello so that your friends will know that we have started. Kindly share the link. Kindly share the link to your friends so that they can also join. Okay. Thank you very much. Okay, so this is how we are going to do it for today. At this juncture, I actually expect you to have watched some of the videos which I have done already, because mechanics of materials is very broad to complete everything. But then most of the stuffs I'm going to do here, I have actually covered some of them already. So please kindly, okay, so what I'm trying to say is that basically I'm going to take you through some problems, but after the tutorials, I have solved some of the problems which you can look at, especially deflection of beams. Okay, all right. So for this tutorial, I'm going to start with curved bars. Okay, I will start off with curved bars. Already, I have done some videos on curved bars, but I will just try to simplify whatever it's about curved bars, and then I'll do bending. So bending and torsion under plastic conditions. So bending and torsion under plastic conditions, and then I will try and look at thin shells or thin walled vessels. So thin walled vessels, where you look at the cylindrical thin cylindrical walls, and then you look at the so the cylindrical and the spherical. Yeah. Okay. So and then if time is there, we will look at mechanical spring. So if time is there, we will look at mechanical springs. But please, I want you to go back and then look at the videos I have already done on deflection of beams. Okay, so I have already done some videos on deflection of beams. Please do well to go over the videos, because I cannot go back to deflection of beams. All right, but it will help you to revise. So go over the videos I have done already on deflection of beams, especially the Macaulay. So kindly take notice of the Macaulay. And then also you should also know how to solve for reactions at the support. Okay, so reactions at the support, the Macaulay's principle, and then also you should know the various ways to do the deflection of the beams. Okay, for instance, if it is a simply supported beam, or if it's a simply supported beam with a uniform distributed load, or let's say it is a cantilever, or a cantilever with a simply supported a cantilever with a load at the free end, or a cantilever which is uniformly distributed. All right, and then also the Castigliano's theorem, or what we call the energy method. Okay, yeah, so basically I think that is it. And then also you can look at the Euler load. So I have done some videos on the Euler load, um both I mean the conditions of the Euler load, looking at whether it's both ends hinge, fixed, one end is fixed, one end is hinge, one end is fixed, the other end is also fixed. So all the conditions available under the Euler load. Okay, we also have what we call the Rankine load, and then the Perry-Robertson formula, and all sort of things happening. So without wasting much time, that's sort of the review of basically what you have done already. So I just want to go through the curve bars with you. All right, so I think we can now start. All right, so basically I just want to go through some of the questions which is already you are already familiar with, and then I will give you the simplest way to go about when you are giving questions about curve bars. Okay, so the first thing I will look at with you is a simple question which I have solved already, but then I will just try and go through with you. Okay, so let's look for our first question. Okay, I'm trying to go through some of the questions I have solved already. Okay, so there is this question which I have solved already, but then I just want to go through it again with you. You can also watch it after the tutorial. So if you sort of look at this question, there is something that I have to explain here. Okay, so let's read the problem together and then solve it. So you have okay, let me clean this one here. All right, so here you see that you have a steel bar which is 50 millimeters in diameter, and this steel bar is formed into a circular arc of 4 meters. So the diameter is 50 millimeters, and then the radius, which is the original radius, is actually 4 meters, but 4 meters is the same as 4,000 millimeters. Okay, and then the question said that it supports an angle of 90 degrees. So if you look at it carefully, you see that the theta, which is the 90, is the original angle. Okay, and then there is a couple which is applied at each end of the bar, which changes the slope to 95 degrees. So basically the new slope is like, let's call it original plus small change. Okay, so let's say that you have a bar which is already here like this, and then you subject this bar to some form of bending, or you apply some some couple or bending moment, so that the angle that is formed here further increases. Okay, so basically that's all what you are saying. One thing that I want you to take notice of is that there is something which we call the neutral axis. So from here I'll be talking much about the neutral axis a lot. Okay, so I'll be mostly talking about the neutral axis a lot. Okay, so when we say the neutral axis is some assumed axis which is passing through the body where the stress is almost zero. All right, so that's basically the neutral axis. One thing that I want you to understand here is that there is the Young's modulus given here as 200 gigapascal. But mostly some students confuse the units when they are changing from one unit to another. Please take notice of this. Whenever you have 200 gigapascal, it is the same as 200 times 10 to the power 3 megapascal. And if you don't do this and you use just the 200, you will get it wrong. So please, whenever you are dealing with some things like this, be careful about the units, because if you just change the units, you will get it wrong. All right. So currently, this question is saying we should calculate the bending stress. Now, this question is the simplest question you can get under curved bars. So if you have a question like this, the first thing you have to do is that you have to look at the relationship between the slope and then the radius. Okay. So if you look at this, there is a formula, and that formula is actually given by, okay, so this is the formula. Whenever there is a change, whenever there is a change in the angle divided by the original angle, then it will be equal to the change in the radius. Okay, it will be equal to the change of the radius divided by the new radius. Now please pay attention to this. When we say that the angle have changed from 90 to 95, all what we are trying to say is that the 95 here is the original plus the small change. Okay, so if it means that if we want the small change, then the small change will be the new which we have, which is 95, minus the original. Okay, but then the original is what? 90. So the original over here is what? 90. So essentially 95 minus 90 is like 5 degrees. Okay, so I mean the small change is 5 degrees. So in this formula that you have here, the small change he's talking about is the change in the angle from the new and then the original angle. Then you divide by the original angle, okay, which is equal to this r here is the original radius, and the question said the original radius was 4,000. So 4,000 minus r1. Now r1 is the new radius. Okay, why are we calculating the new radius? If you don't calculate the new radius, you will not be able to calculate the change in the how do I put it, the strain. Okay, so the strain in the bar is a function of the radius. So if you don't calculate the new radius, you cannot be able to calculate the strain. So as a matter of fact, we are after this new radius. Now when you get to this point, it is no more strength of materials, because at this point all what you have to do is to make R1 the subject, because once you're able to find R1, which is the new radius, you'll be able to calculate the strain or the bending stress. Okay, now from strength of materials 1. So please, I want you to do this and give me the answer. As a matter of fact, if you do everything correct and then go through the calculation, you will end up getting 3789 point something. But you, okay, let's do it together quickly. So you have 5R1 should be equal to 90 multiplied by 4,000 minus 90 multiplied by R1. Okay, so if you add the R1 together, you get 95 R1 should be equal to 90 times 4,000. Dividing both sides, you can see that R1 will be what? 90 divided by 95 multiplied by 4,000. And if you do everything correct, basically you are going to get so it's going to be 90 divided by 95, then you multiply this by 4,000, which is basically going to be So 3789.47, or let's, okay, 3789.47. So 3789.47. So that is actually the new radius that you are going to get. Why are we calculating this? Because we know from strength of materials 1 that the stress is strain multiplied by the stress is the Young's modulus multiplied by the strain. But then the strain is going to be a function of the fiber distance. Okay, I'm going to explain fiber distance very soon. So actually what you are going to do is that when you get to this point, all what you are going to do is you just quote the formula, and I'll give you the formula straight away. So it's going to be 1 over, so actually when you get to this point, it's going to be y multiplied by 1 over r1 minus 1 over r. Y multiplied by 1 over r1 minus 1 over r. So please pay attention here. What you have here is the strain. So this quantity here is the strain in the bar. This quantity here is the strain in the bar. But if you multiply the strain with the Young's modulus, then you get the stress. Okay, so if you want to get the stress, then it's going to be 200 times 10 to the power 3, which is the Young's modulus, by the y. So let me teach you the y. When we say the y is like the fiber distance. Okay, so ask yourself, if you have this member like this, and then this is the neutral axis which is passing through the body like this, then the fiber distance y will be moving from the neutral axis. So the maximum of the fiber distance will be at a distance which is at the surface. Okay, and mostly for a circular cross section, it's going to be the diameter divided by 2. Okay, we are going to solve some couple of questions very soon, then you understand it better. But for a circular cross section, okay, let me bring it here. So what I'm trying to say is that for a circular cross section, the neutral axis is always the diameter divided by 2. The fiber distance. So that is the y. Fiber distance. So if you put this one here, it's going to be the diameter. And from the question, it says that the diameter was 50 millimeters. So that is the 50 millimeters here. And then all what you have to do is to just, so 50 divided by 2, and that is the y. Then you multiply the 25 or the 50 divided by 2 by 1 over the new, and the new we had what? We had 3789.47. So 3789.47 minus 1 divided by the original, which is what? 4,000. So the original radius is 4,000. So basically, the actual stress due to the bending will be what? So it's going to be 200 times 10 to the power 3 multiplied by, so 50 out of 2 is 25. Then we multiply this by 1 out of 3789.47, and then minus 1 out of 4,000. Then you close this. So you end up getting 69.45. And basically that's the bending stress. So 69.45 Newton per millimeter square, or megapascal. So this question has been solved. You realize that for this question, we just have to calculate the new radius and then put the new radius into this equation. Okay, all right. But sometimes the question can be difficult. So let's move on to the next question. Is there any question up to this point? Please, you can leave it in the comment section. Is there any question up to this point? So is there any question up to this point? All right, so let's look at the next problem. In this problem, I want to explain some concepts here for you to understand. And then I'll give you what we call the link radius. So already I have solved the question, but I would like to go through again with you. Okay, thank you. So let's look at the curve bar question, which involve what we call the link radius. So let me delete what I have done and then solve it again with you guys. All right. So in this question, you have been given a curve bar, which is more or less like of a square section. Okay, and then it is 3 meter sides. So think about this as some sort of square, or let's say a rectangle. Okay, but then this one is, in terms of millimeters, 30 millimeters by 30 millimeters. Okay, now the radius of curvature is 4. So 4.5. So r, which is the radius of curvature, is 4.5 centimeters, which is the same as what? So the r is basically the same as 45 millimeters. Okay, now there is a bending moment of 300 Newton meter. So the bending moment, which is the m, is 300 Newton meter applied to the tendon to straighten it. So find the stress at the inner and outer surface. So this question is kind of how do I put it? It may confuse you, but actually it's very simple and straightforward. Okay, this question is actually simple and straightforward. The best way to understand this is to think of a beam. Okay, so think of the beam as something like this. Let's say this is the square beam. Okay, and then there is some form of bending. Okay, there is some form of bending. Now if that bending occurs, you are going to end up getting something which looks like this. Okay, so initially your beam was straight, But then, due to the application of some bending moment, the beam now became it actually turned into that slope. Okay, so then there is this form of neutral axis which is going to form. Okay, so again the neutral axis will come. Now please pay attention. When we stretch a beam like this the top surface here will be compressed, so compression, but the bottom surface here will be in tension. So that's all. The surface here will be in compression, this surface will be in tension. So normally what we do is that we call something the fiber distance, which is y. So y is equal to fiber distance. So essentially, if we move in a direction which is going up here, okay, then we assume that we are in minus y, okay. But if we move in a direction which is coming down, so if we move in a direction which is coming down, then we call that positive y. So that's all. Y is called the fiber distance. If I move in the direction upwards, then it is called minus y. And then if I move in the direction downwards, then it's called positive y. That's all. Okay. So now, at this juncture, I want to show you something. Okay. I want to show you something. First of all, let me write the stress equation. So there is a horrible formula. Memorize the formula. But if you want to memorize, then it's up to you. So the formula is given by m over ar into bracket 1 plus r square y, all divided by okay, I was trying to memorize it, but I have forgotten. So let me go back and watch the equation. So in effect, the equation is, yeah, so I didn't add h squared, so h squared r plus y. Now this is where the students find confusing. There is something which we call h square. So the h square here is what we call the link radius. There are several formulas on the link radius, but please don't worry yourself trying to understand all the equations and the link radius and whatever have you. Forget about whatever is in there. All what you have to pay attention to is that when they give you a question on curved bars, please look at the cross section. If it is a rectangle, there's a formula for the link radius. If it is a triangle, there's a formula for the link radius. If it is a circle, there is a formula for the link radius. If it is a trapezium, there is a formula for the link radius. What am I trying to say? Any cross section has got a formula for the link radius. So you don't have to go to the library spending the whole night trying to understand the formulas for the link radius. Just know that, okay, if it is a rectangle, which one applies? If it is a triangle, which one applies? That's all. That's all. Okay. So now, this is a square. This question is about a square. And you know, a square is like, let's say, a rectangle. Okay. So basically, all what you have to know is to know the formula which can give you the link radius for a square or a rectangle. And that formula is simple. So that formula for the link radius is very simple for a rectangle. So if you have a rectangle, that formula will be, so let me quote that formula. So 2.3 2.3 multiplied by the cube of the radius of curvature divided by the depth, okay, divided by the depth, and then the length. So this is where it confuses people. I will talk about it later. So 2r plus d divided by 2r minus d. After doing all this, then minus r squared. So I don't expect you to memorize this formula, but if you want to memorize, it's up to you. As a matter of fact, all these equations will be given, but if you don't understand how to use them, you will not even know that you have been given the formulas. Okay, so please, this is what we call the link radius. Now I'm coming to explain the equation, the symbols. So the 2.3 here is like a constant. Okay, the 2.3 here is like a constant, and then r cube over d. So the r is the radius of curvature. So for this question, the radius of curvature was 45 millimeters. Okay, and then the depth. So the d. So please pay attention. When we say d, it means the depth. Okay, d is the depth. So what is the depth? If you look at this beam, the depth is that side which is here. In other words, this side is the depth. So even if it is a rectangular cross section, the d will always represent the depth. Okay. So all the time, whenever you see d, it means what? Depth. That's all. Now you will see that we have done everything. So m here. So the m is the bending moment, or sometimes it is called the couple. Okay, so the m is the bending moment or the couple. That's all. So this m here. Now from the question, the bending moment was 300 Newton meter. So since we are dealing with millimeters, 300 Newton meter will be 300 times 1000 millimeters, which is the same as 1 meter. Okay, because we are converting everything to millimeters, so that whatever answer we will get will be in what? Megapascal. Okay, all right. So now what are we going to do? Essentially, we have everything that we can use to solve the equation, but the a is also the radius, the area. So before we calculate this, okay, let's calculate the link radius first, and then I'll continue with the equation. So h squared will be 2.3 r, which is 45 cube. Then I divide it by the diameter, the depth, which is so the depth is, like I said, this side. So this is the d, and then it's actually 30. Now length, please, in some of the textbooks you will see log instead of length, but it is actually length. It is not log. Please, it is length. It is not log. Because if you say log, you'll be confused. Okay, log means log to the base 10, but length means log to the base e. Okay, so pay attention to this. It is always length, not log. But sometimes some of the programming languages, if you write log, it means length. But in this context, we are dealing with the natural logarithm, not the log to the base 10. Okay. So 2 times the radius of curvature, which is 45, plus the depth, which is 30, divided by 2 times the radius of curvature minus the depth, which is 30, and then minus the radius of curvature squared, so 45 squared. So now h squared will be, so let's calculate this together. So basically we are going to get 2.3, and then we multiply it by the fraction. So 2.3 multiplied by the fraction 45 cube, then we divide by 30. Okay, so if you divide by 30, then that is where the ln will come. So please, it is the ln, not the log. And then a fraction will come. 2 times 45 plus 30. The same thing. 2 times 45 minus 30. And then, so you do minus 45 squared. Now, if you do this correct, I think there is a mistake somewhere, because we are supposed to get okay, let me check again. So 2.3 into this ln of the radius of curvature okay, oh no, we are not supposed to. Let me kindly go over the equation again. So pick your calculators and let's do this together. So okay, I think there is a So let me clean this. Let me clean this 2.3 from it. I think that is what is causing the mess. So I want to correct this. There are two formulas to calculate the h squared for the rectangle. If you bring the 2.3, then you actually use, so this is what I'm saying. There is a formula which is 2.3 multiplied by r cubed over d log 2r plus d divided by 2r minus d minus r squared. So this is one formula, okay? And there's another formula which is h squared r cubed over d, then ln 2r plus d 2r minus d minus r squared. But actually that is it. If you are using okay, yeah, so that is it. Basically you just have to ignore the 2.3, but if you want to use the 2.3, then you have to use the equation which has the logarithm in it. I hope the concept is clear. So the answer is actually supposed to, I am not supposed to add the 2.3 in front. Yeah, so the actual answer is 80. So the answer is 80.435. Please, any question? The whole idea is that if you use, you see, this is the confusion. If you use 2.3, then essentially you just have to use the log. I think that is all. So that's why there was a confusion. All right. Yes, thank you. So there are two formulas for the same. Okay. Now, so the answer can either be 70. Okay, let me do that one too. So if you use the 2.3 here, you rather come here and use log, okay? And that will give you 78, okay? So that's basically going to give you 78.07. But as far as I am concerned, these two are correct, depending on what you are looking at. But which one do you like? Do you want the one with the log or the one which you don't have to use, or the ln actually? Which one do you like? The log or the ln? Okay. So that is basically the h squared. But we are not actually interested in h squared. We are looking at h squared because there is something in this formula here. So let me copy it again. Okay. So someone said learn. Okay. So basically if you look at this formula here, the h square here, that is why we are suffering. In fact, this formula is supposed to be simple and straightforward, but we are suffering all because of the h squared, because that is the link radius. Okay, so let me teach you one thing. Let's come back to this diagram. If you are looking at the top surface, and then the outer, so inner and the outer. Okay, so the inner and then the outer surface. Okay, so basically, if you look at this part is called the inner surface, and then this is the outer surface. So essentially, for the inner surface, okay, the y or the fiber distance is taken as negative, and then for the outer, for the outer surface, the y is taken as positive. In other words, inner surface is the same as compression, and then outer surface is the same as what? Tension. Basically, that's all. Okay, so inner surface is this, and then the outer surface is that one. So without wasting much time, what will be the area? So the area of a square is going to be 30 millimeters by 30 millimeters, which gives us what? So 30 by 30, which is the same as 900 millimeters squared. So in other words, the area is 900 millimeters squared. Okay, we have the area, we have the moment. So for the inner surface, we will choose, okay, again. So again, the y, which is the same as the fiber distance, will be given as what? D over 2, right? Because the neutral axis will divide the beam into 2 equal halves. So y will always be d out of 2, but the d is always the depth. Okay, so in this case it's 30, so it's going to be 15 millimeters. So essentially y will be 30 over 2, which is 15 millimeters. So that is why. But when you are dealing with the inner surface, y will be minus 15 because of the compression. Okay, then you quote the equation. So moment is 300 times 1000 divided by area, which is 900, that is 30 by 30. The radius of curvature is 45, and then you multiply it by 1 plus the square of the radius of curvature multiplied by y. So minus 15 because of the inner surface or the compression. Then you divide this part by the link radius, which we are looking at. So you can either use, so I'm using the length. So if you use the length to calculate, it will be 80.435. Okay, but in exams, either of them that you use is correct, but I want you to use the one that you are okay with. If you want to use the one that is in your slides, that's okay. So we have this h squared, then r plus y. So 45 minus 15 because of the compressive. Now you are going to do the same thing, but then for the outer surface, the y will become plus 15. Okay, so if you come back here, the outer surface is where the y will be what? Positive. Okay, So if the y is positive, then ideally, if the y is positive, then that is what? Tension. But if the y is negative, then that's what? Compression. So ideally, that's basically what happens. Okay. So we are done with this part. All what you have to do right now is to calculate it direct, which is going to be so essentially it's just going to be the same thing, but you are going to negate. So 900 multiplied by 45, 1 plus 45 squared. But this time around, instead of minus, it becomes positive. Then you divide this part by 80.453, 45 plus 15. So what are you going to get? So let's quickly do this. So it's going to be 300 multiplied by 1000 divided by 900 multiplied by 45. Then I multiply here by 1 plus 45 squared multiplied by minus 15 divided by 80.453 multiplied by 45 minus 15, and then you close the bracket. So if you do it for the negative, you get minus 85.814 megapascal. But if you do it for the positive, you just have to so essentially you just have to change the minus here to become plus. Then you come to the top part here. Then that one becomes plus. Okay, I don't need to do that, but so 54.01018 or 54.02. Okay, so please, any question up to this point? So whenever you have a curve bar question, all what you have to do is to know the formula for the link radius. Okay, just know the formula for the link radius. If you know the formula for the link radius, you'll be okay. But it's up to you. For the rectangle, you can either use the one without the line, the one with the line or the log. But as a matter of fact, the one that I have known that it is good is the one with the line. So please, any questions? Any questions before I move to the next one? Please, any questions? Okay. Okay, so now I want us to look at another scenario. Okay, let's look at another scenario. So I hope now you get the concept. Let's the same concept, but then this time round, let's say you have been given a circular cross section. So this time round, it is not okay. So in this problem, you have been given a beam of circular cross section, which is what? Diameter is 20. Then the line, center line curved to a radius of what? 50 mm. So diameter is 20 mm. Radius of curvature is 50 mm. Now we've been asked to find the intensity of maximum stresses in the beam when subjected to what? So the moment or the bending moment is actually 5 kilonewton per, okay, so kilonewton millimeter. So essentially the moment is 5,000 Newton millimeter. Okay, so with this question, it's actually the same problem. Okay, we are just going to do the same thing. So the stress will be M over AR into bracket 1 plus H squared Y, no, R squared Y, H squared, let me go back and look at the formula again. So R squared Y over H squared into R plus Y. Okay, so essentially you see that for this problem too, basically it's the same thing. But then let me give you a hint. A hint. You know, the hint is that look for H square for a circular cross section. So essentially, this question is the same as the last question. The only thing you have to do here is to basically go and find out if there is a formula for H square. If you have, how do I put it? So when you are given a circular cross section, do you have a formula for H square? If yes, then just come and put it here. Everything is the same. That's all. So without wasting much time, let's go ahead and then solve this question. So first of all, so this is it. We have this form of circular cross section, something like this. Okay, so there will be this neutral axis here. And I told you already that there is fiber distance. Okay, I think I should rather do it this way. Or any way I draw it does not really matter. The whole idea is that there is always a fiber distance, which is y. So let me bring it here. So there is always y. Now the whole idea here is, for now I'm not going to do the whole thing again. If it is compression, it is negative. If it is tension, it is positive. That's all. So all what I'm trying to say is that the fiber distance is y, which is what? The depth over 2. But this time around, the shape given is a circular, cross section. So basically we are going to use the diameter. Okay, so we will use the diameter. So essentially it's going to be 20 divided by 2, which is like 10. So again, y will be plus or minus 10 depending on the stresses that they want. So this question said we should calculate the maximum stresses. So you can either say sigma 1, sigma 2, or compression and tension. But let's say sigma 1 could be the one of the stresses. Anyway, let's calculate h square, because if you don't know h square, you cannot solve it. So let's go back and look at the h square for a shape which is circular. So the formula for the h squared is given by, if I have a circular cross section, it is given by d squared, so d squared over 16 plus 1 over 8 multiplied by d to the power 4 divided by 16r to the power so r squared. And then so basically this is some sort of the equation you have to use in order to calculate the link radius for a circular cross section. So like I said, nothing has changed. Okay, nothing has changed. The whole idea is that you have to look for the link radius. Once you are able to calculate the link radius, then to get the stresses, it's just going to be plus or minus y. That's all. So you see how the curve bar is very simple. All right. Okay. So basically the link radius h squared is going to be d squared. Okay, so the d squared is going to be now what is the d here? The d is actually the diameter. Okay, the d is the diameter. For this question, the diameter was 20. So 20 squared divided by 16 plus 1 over 8 multiplied by 20 to the power 4 divided by 16. Now the r here is actually the radius of curvature. Okay, now the question said it was curved to a radius of 50 millimeters. So basically the r there is some sort of the radius of curvature. Okay, so essentially it's going to be 50 squared. So let's calculate for h squared. So to calculate for this one, it's going to be 20 squared divided by 16 plus 1 out of 8. And then I'll multiply this by 20 to the power 4 divided by 16 to the multiplied by 50 to the power, no, 50 squared. And this gives us 25.5. Wow. Now, when you get this, it's actually in millimeters. Then you realize that we have actually solved the question. Because right now, all what we have to do is to go back and put whatever we have into the stress equation. But let's calculate the area. You know, the area is actually, so what is the area of a circular cross section? Very simple, isn't it? So it's going to be pi d squared over 4. So essentially pi times 20 squared over 4. And what is that? So essentially pi times 20 squared over 4. That's all. So basically you are going to get 314.16 essentially. 314.16 millimeter squared. So that's the sort of the area of the you know, the area of the cross section or the cross sectional area. So we can go ahead and find the stress. Okay, so I will just copy the equation. Okay, so right now we have everything that we need to solve. So sigma 1 will be the m, okay, which is what? So the moment was 5,000 and the area so 314.16. R is so R is 50. Okay, R is 50. Now so it's going to be 1 plus 50 squared, and then the y is what? So the y is okay, so for sigma 1, y will be negative. That's like the compressive stress. So minus 10. So minus 10 divided by h squared. So the link radius, we have calculated it already. 25.5. So 50 minus 10. So essentially, the first stress is going to be what? So 5,314.16 multiplied by 50. 1 plus 50 squared multiplied by minus 10 divided by 25.5 into 50 minus 10. So that gives us minus 7.483. So minus 7.483 mega Pascal. So essentially, you have your sigma 1 over there. Now to calculate your sigma 2, all what you have to do is that you say that for y is what? Plus 10 millimeters, and then everything is the same. You just have to only negate, make it positive rather. So 5,314.16 multiplied by 50, and then 1 plus 50 squared into 10 divided by 25.5, 50 this time around plus 10. Then you close the bracket. Now if you do this correct, you are going to end up with what? So just maintain everything, but then this time around here is plus. That's all. So you get 5.52. So these are the stresses. Any question up to this point? So I want to look at one last application question which sometimes come in exams. And then it's going to be on crane hooks. Okay, so I just want to solve, because actually we are done. We just have to look at some simple examples. Okay. Okay. So okay. So please, any questions? So I just want to solve one crane hook question with you, and then we will end it on curve bath. Okay. All right. So I am moving to the crane hook question. So sometimes there is some application of application of the Curve bar. Okay. So let's look at the crane hook question. Okay. All right. So there we are with a crane hook question. So this is actually a direct application of the uh so the direct application of the curve bars actually. So we've been asked to find um some of the stresses in the crane hook. So let's look at this question. Okay. So to better understand this, all right. So that's the question there for you. Okay. So in this question, what do you see? You see that there is this sort of crane hook, but then it's having a trapezoidal cross section. Okay. But then we have every information here. So all what you have to do is to calculate the stresses. So the compressive and then the tensile stress. Okay. So the first step here is to look at the cross section. So let's look at the cross section together. Sorry. All right. Now, if you look at what we have here, you will see that so a crane hook carries a load of 5 kilonewton. And then what else? We have been given that the load is at a horizontal distance of 32 millimeters from the inside edge of a horizontal section through the center of curvature. All right. So interestingly, there is this O here. Okay. And then you can see that there is a load of 5 kilonewtons. But then this load is having a line of the line of action which passes through this body like this. So that is the 5 kilonewton there. But then it is at a distance. Okay, so if you take this cross section and then you cut it out, you see a trapezium, and that is what they are saying. So basically, this is like if you look at the plan, or if you are standing at the top and you are viewing from the top, you will see this as a trapezium. Okay, and all the dimensions of that trapezium has been given to us. So we have y1 and we have y2. So essentially, y1 and y2 is nothing but the centroid of the trapezium. All right. Okay. So right now we have to look at the trapezium and then look at all the sort of analysis using the trapezoidal cross section. Don't forget that I told you that the link radius is actually applicable to all the cross section. So each cross section comes with the link radius. So each cross section has a link radius. That's all. So bear that in mind that each cross section has a link radius. Okay. Now if we look at this figure here, you will clearly see that this figure which we have here, okay, that is where I want us to look at right now. So let's define some terms. The R which you see over here, okay, this R, if you look at the diagram, you can see that there is y1 and there is y2. So the distance from the point here to meet the the center line or the O is actually R. But then there are two axes. You can see that there is the centroidal axis and then there is a neutral axis. Okay. So this question is confusing, but I want you to pay attention here. You will see that. So the best way to look at it is, the best way to look at this is that think of this trapezium as having some um centroid, and then it will pass through a certain distance. Okay, and then also there is a neutral axis. Okay, and all of them will pass through. Oh, sorry about that. So let me work on the microphone. Okay. Okay, can you hear me now? All right. So what I was trying to say is that, hello? Can you hear me, please? Can you hear me? Okay. So in effect, um, what we have here, um, let's okay. Let me just go through the solution with you. So first of all, we have to calculate um so first of all we have to calculate the y1 and then the y2. Okay. Once we have the y1 and the y2, we can come back and use the stress equations. Stress equations. All right. Okay. Okay, so let's continue. So at this point, all what we have to do, okay, let's calculate y1. So if I say y1, y1 here is more or less like the okay. So what I'm trying to say is that there is y1 here and there is y2. So if we take this cross section, we can calculate the centroid. And what is the centroid of a trapezium? Centroid of trapezium. Okay, thank you. Thank you. Now for the centroid of the trapezium, we need to use a certain formula, but I will give it to you. We will first of all calculate y1 and then we will calculate y2. So let's start from y1. So first of all, the centroid of a trapezium is given by b1 plus 2b2 divided by b1 plus b2 multiplied by d out of 3. Now, essentially, why are we calculating this? I want you to pay attention to this. If you look at the trapezium, a trapezium is like this. Now we know that the depth is from here to here. That's the depth. Okay. But the actual centroid is somewhere at a distance y1. But we want to calculate the y2, because if you look at this here, so we can clearly see that if we add y1 plus y2, we will get d. But the y1 is the centroid, so that y2 will be what? D minus y1. So we just have to go straight forward and calculate y1, which is the what? Centroid of a trapezium. The centroid of a trapezium is given by so a trapezium will have two horizontal sides, or let's say so two vertical sides, in a way you want to look at it. So here is b1, here is b2, the longest length, the shortest length, b2, and then you just look at this, and then the depth divided by 3, then you get the centroid. You can also look at this as a trapezium as what? Two triangles, and then what? So two triangles and then a rectangle. So the d over 3 here is because it is actually a triangle, and for triangles the centroid will be at a distance d over 3, or 1/3 from the base, 1/3 of the height. So let's put the formula, let's put the values inside. b1 is the longest side, which is what? 26. If you go back to the cross section, this is 26. So b1 is 26 plus 2, b2, which is 13. Then we divide this by b1 plus b2. So b1 plus b2, which is 13 plus 26, multiplied by the depth. Now the depth is actually this distance all the way through here, and that is 32 from the diagram. The depth is 32. So y1 will be what? So if you put everything inside, y1 will be 26 plus 2 multiplied by 13 divided by 13 plus 26. Then you multiply this by what? 32 divided by 3. So we are going to get 14.2, or let's say 14.22 in millimeters. Okay. All right. So now our y1 is here. Therefore, our y2 will be 32 minus 14.22. And that will be what? So 32 minus 14.22. 17.78 millimeters. So that is it. Y2 is 17.78, and that is it. Now why are we doing y1, y2 and all these things? We will soon understand it. Okay. So now that we have y1 and then y2, let's calculate the r1 and then r2. So let's calculate r1 and then r2. So r is this distance from here all the way up to here. That is to say, the radius of curvature r. If you come to the diagram, then you ask yourself, what is the r? Clearly speaking, you will see that the r is nothing but what? So the r is actually so the r is 38 plus the small distance. Okay, I'm coming. So when we say r, so this is what I'm trying to say. When we say r is from here to here. Okay? And if you want to get from here to here, we can all see that r will be r1 plus y1. Look at it carefully. You will see that r here is y1 plus r1. As for r1, we don't have to calculate. r1 is the distance from here to here. If you look at the diagram, this is O. Here is 38. So it means that if I draw any distance to meet here, okay, so this is what I'm saying. The inner radius is r1, okay, and the outer radius is r2. Now, if I want to get the inner radius, it's simple. I just have to calculate the distance from here to here. Okay, and that distance is the same as distance from here to here. So r1 is 38 millimeters. But then the r is actually what goes inside. So r means r1 plus y1. So okay, r1 is 38 millimeters. That is to say the inner radius. Therefore, our r, which is the radius of curvature, will be 38 plus 14.22. So what is 38 plus 14.22? That is going to be 52.22 millimeters. Okay. Now, this 52.22 will be the r. But what is r2? So if we want r2 is the radius of the outer edge. So that is to say, we are going to add 38 plus 32. So let me show you. When you go back to the diagram, r2 is nothing but d here and then r1. So from here to here is r1, and then from here to here is d. So r2 is going to be what? D plus r1, but the d is what? 32. So it's going to be 32, which is the d, plus the r1, which is what? 38. That's why I said r2 is d plus r1, which is 32 plus 38. So 32 plus 38 is 70. So 32 plus 38 is 70 millimeters. Okay. All right. So basically, this is R2. But why are we doing all these things? Don't worry. You'll see it very soon. So let's ask ourselves now, if you want to calculate the stress of the trapezium or the cross section, there's a formula which we have to use. And this formula, let me write the formula. But before we look at the formula, we have to calculate the link radius. So guys, we want to ask ourselves, what is the link radius for a trapezoidal section? So what is the link radius for a trapezoidal section? Or let's say a trapezium. This formula is a horrible formula which is very, very, very long. And please, don't memorize it. It will be given to you. So don't bother yourself trying to memorize it. Okay. Now let me write the formula for you. So the link radius formula for a trapezium is given by h squared equals so h squared is equal to r cube divided by a. So let me write this. R cube divided by a. After doing this, then you multiply the whole of this by log R2 over R1 into bracket B2 plus, so B1 minus B2 divided by D multiplied by R2 and then the inner bracket will be closed, but then minus B1 minus B2 bracket close, all minus R square. So guys, this is the formula for the link radius when you have a trapezium. So this formula is only used when you are dealing with a crane hook question. And this question is a typical exam question. This is a typical exam question because this is like a full question on its own. Okay? This is a typical question. So please, take your time and go through this question. Okay? All right. Now, we have been able to come up with the equation. So let's put the values inside. Okay. So h squared will be r cubed. Now we know r is what? 52.22 cube divided by a. A is what? So a is the area of the trapezium. Okay. So if you have a trapezium, the area of the trapezium is given by, okay, let me calculate the area. So the area of a trapezium is given by d out of 2 multiplied by b1 plus b2. So this is the formula for the area of the trapezium. So it's going to be, the d is going to be 32. So d is this distance here, okay, and that from the diagram is actually 32. So d is 32. 32 divided by 2, 13 plus 26. Don't forget that b1 and b2 was what? 13 and 26. So effectively, we have been able to calculate the area. So let's put this into our calculator. 32 divided by 2 multiplying 13 plus 26, and that gives us 624. So the area is 624 millimeters squared. So now, if you want the link radius, you have to put everything inside. So 52.22 cube divided by area 624 into log of r2, which is 70, divided by r1, which is what? 38, right? R1 is 38, yes. Then the bracket will come b2. So b2 is what? b2 is 13 plus b1, which is 26, minus b2, which is 13, divided by d, which is 32, multiplied by r2. R2 is 70. Then minus. So b1 minus b2. So b1 is 26 minus 13. Into this minus r. So r is what? 52.2. Squared. All right. So this is the horrible formula that we have. Have you seen this question before, guys? Have you ever seen this question before? So at this point, I want you to do this on your calculator and calculate h square. And if you calculate h square, what are you going to get? So if you do everything correct, um so this is a typical exam question, so please take notice. And after the tutorial, it's going to be recorded so you can play back and then watch. So 52.33 divided by 624. So, oh no, 52.22 cubed. Then you multiply the whole of this by log of 70 divided by 38. Then you put that into bracket. And then that same log of 70 over 38 will open again and come and multiply 13 plus 26 minus 13 divided by 32 multiplied by 70. So there will be a bracket which will be closed here, but then minus 26 minus 13, and then another bracket will come. Now if you do everything correct, I think there is a problem with this calculation, but whatever we have here is correct. So if you put everything correct inside here, you are going to get somewhere around 82.9. So I want you to go back and look at it again. But then okay, I don't know if I have done some mistake somewhere. Okay. So take your time and cross check the answers. But then the answer is supposed to be 82.9. I've already calculated it, but I don't know why I'm getting this. So I'll leave that for you to verify that. Now, there is a formula which we have to use to calculate the stress. So this is the formula, another horrible formula. The stress will be W over area all into 1 minus X over R one plus r squared, and then what? Y, and then h squared r plus y. So it's going to be like, looks like it's similar to the equation which we did, we used earlier on, but then some slight modification. So now, if you want to get the stresses, don't forget that we have y1 and we have y2. Okay, so y1, what did we get? We got 14.22. And then y2, we got what? 17.78. So this y1 that we have here, and then this y2 that we have here, we are going to use those two to solve for the stresses. Okay, we are going to use those two to solve for the stresses. So first of all, we are going to assume that at the inner surface or inside the inner edge, then okay, let me go back. So if you look at here, what do you see? So you can see that the 14.2 goes inside, and then the 78 comes outside. So in other words, there is a thin line here, and then this is the direction. Okay, as a matter of fact, you can see that the neutral axis is this axis here. So please, this is the convention. The y1 will be negated, and then the y2 will be positive. In other words, y1 will be minus 14.22, and then y2 will be positive 17.78, so that we can use it to calculate the stress. Let me go over this again. If you go back to the diagram, y1 is moving inside, and then y2 is outside, because this is the neutral axis. Okay, this is the neutral axis. Or as a way to memorize it, y1 is negated and y2 is positive. That's all. Once you have done this, then you go back to the equation. So the W there is a load. So let's go back and look at the load. So the load was actually a 5 kilonewton load that was placed on the crane hook. So that one will be 5. In other words, 5,000. Then I will divide this by the area. The area was what? The area of a trapezium. We got 624. This one. So, okay, so divided by 624 into bracket 1 minus x over r. So this is also one thing that you have to look at. The x, in this case, is going to be 38. Because if you look at the diagram, So if you look at the diagram, the x is this distance, but then you can see that we have x2 and then we have x1. Okay, but then the x in this case for the y1 is going to be 38. Okay. So 38 divided by r, which is 52.22, and then into bracket 1 plus r squared. So r squared is what? 52.22 squared. But because we are dealing with the first stress, here will be minus 14.22. Then I will divide this by what? H squared, which is 82.9. Then I will multiply here by what? R, which is 52.22, and then minus 14.22. So this is what we have here. Now, if you do everything correct, your stress will be around somewhere 73.82. Sorry. Okay. So someone said the log should be multiplied by 2.3. Okay. So if you know what to do, then that is it. Okay. Thank you, Olivia. Thank you. But then I hope the concept is clear. Okay. Because all these are formula work. So if the formula is wrong, automatically your answer is wrong. And then for the second stress, it's going to be the same thing. But then when you get to this point, all what you have to do is to change it and make it the y2. Okay. So 38 over 52.22, 1 plus 52.22 squared, 82.9. But this time round, it's going to be plus 17.78 divided by 52.22 plus 17.78. And then if you do everything correct, you should get somewhere minus 46.58 megapascal. So essentially, this question is some application which you can get from the it's one of the applications you can get from the curve bars, bending of curve bars. So there are some other questions which have a chain link and all those sort of things. I don't want to solve the the chain link questions with you, because mostly if a question will come in exams, it is mostly going to be the crane hook. However, the concept is the same. So all you have to do is to know the formula for the crane hook. Sorry, all you have to know is to get the formula for the link radius. Once you have the link radius, you just have to find the link radius. After getting the h square, then you put it into the stress equation. But then the first ones that we were dealing with was simple. But with the application, you have to know if it's a crane hook, you have to use the trapezium. If it's a chain link, there's another way to do it. But that one is long. So please, if you have some time, spend some time and go through that. Okay? Do you want me to solve chain ring question with you? Because ideally, a typical exam question will be the crane hook. But the same idea applies to all of them. Just know the link radius. Once you know the link radius, understand the equations which apply and take your time and solve them. That's all. Or do you have any other questions on this? Okay. Um okay, maybe let me do it. Let me just do it with you. Or should I? Right now I want to go to 10 word vessels, and then I'll come back to bending and torsion under plastic condition. But then the time is already spent. So do you want me to do more, or we can end? Okay. Someone said mechanical springs. Okay. So let's look at mechanical springs. Let's look at mechanical springs. And then maybe I will look at the tin word and all those things. So again, you have to understand that everything is all about formulas. Everything is all about formulas. Okay. So the first thing I want us to do is to look at something here. So the first thing I want to look at is when we have semi-elliptic leaf springs. So mostly a leaf spring is common with when you have automobiles. Okay. So we are going to use some formulas. So all you have to do is to know the formulas and then what they mean. Okay. So let's say that if I have a leaf spring, it will have a length or span, some thickness T. So L is the span or the length, T is the thickness, and then B is the width, and then N is the number of plates. W is the load acting on the spring, and then maximum bending stress is sigma. I mean the maximum bending stress developed in the springs. Okay, and then the original deflection of the top spring, and then R is the radius. But let me give you a hint. So if you want to treat leaf springs, treat them as though simply supported beam, which have load some kind of reaction support at the end. Okay, so if you have, I mean, something like this, treat it as a simply supported beam. Okay, the rest is just using the formulas to solve questions. That's all. And then I'm not supposed how do I put it? I'm not really asking you to sort of memorize the equations. Okay, because the equations are many. Just know how to use them. That's all. So maybe let's look at a simple question here. All right. Okay. Um. So let's look at this simple question. We have a laminated spring, which is more or less like a leaf spring. So a leaf spring of span 1 meter long. So the length is what? 1 meter long, which is the same as what? 1000 millimeters. It's made up of plates, each with what? Weight. So the weight is B, which is what? 50 mm. And then 10 millimeters thick. So the thickness is T, which is what? 10 mm. Now, if the bending stress in the plate is limited to 100 megapascal, so meaning that the maximum bending should not exceed 100 megapascal. How many plates are required to enable the spring? So how many plates? Number of plates is required to carry a central point load, so W, 2 kilonewton. Now, if the modulus of the elasticity of the spring material is 200 GPa, then so 200 GPa is the same as 200 times 10 to the power 3 megapascal. So what is the deflection? So the same question, but it's asking what? Two questions. First of all, we have to calculate the number of plates, and then we also have to calculate what? So the number of plates and then the deflection, right? Okay. Um okay. So let's solve this question. How can I find the number of plates? So basically everything is just a formula work. To calculate the number of plates, we have to find a relationship. Okay. So there is an equation which we can use, and I want to quote that equation right now. So one thing that you have to understand is that, number one, the stress in the leaf is equal to 3 times the weight and the span divided by 2 multiplied by the number of plates and then the thickness and then the weight and then sorry, 2n b t squared. So this formula means that if you have the stress and then you can calculate n. So let's make n the subject. So the stress was 100, the load is 2000 newtons, the length or the span is 1000 divided by 2 multiplied by the number, the width is 50, the thickness is 10. So if you make n the subject, then you get the number of plates. So it's very simple. You just have to know the formula which applies. So making n the subject, n will be what? 3 times 2000 times 1000 all divided by 100 times 2 times 50 times 10 squared. And what is that? So what are we going to get? Okay, let me take my time and do it. So when you cross multiply, it's going to be 100 times 2n times 50 times 10 squared, which is equal to 3 times 2000 times 1000. So if you make n the subject, it's going to be what? So n is going to be 3 times 2000 times 1000 all divided by 100 times 50 10 squared and then 2. Therefore, N will be what? So 3 times 2000 times 1000 divided by 100 multiplied by 50 times 10 squared times 2. So N is 6. It means that we need what? 6 plates. So the number of plates is what? 6 plates. And then we have been asked to calculate the deflection. So what is the deflection formula? Simply straightforward. Without wasting much time, we also know that the deflection under the load. So there are two ways. You can either solve using the stress and then the Young's modulus, or you can use the load. So this is what I'm saying. The deflection can be given as sigma L squared divided by so sigma L squared divided by 4 ET. Or you can also use this equation. 3W L cube. So 3W L cube divided by 8 EN BT cube. So either of the equations will give you the same results. But if you are given the stress, then you can use the stress equation. However, if you don't have the stress, you can still use the load to calculate. But we have the stress, so we can just go ahead and say that it's going to be what? 100 megapascals times the length, which is 1000 squared divided by 4 times the Young's modulus, which is 200 times 10 to the power 3. Then you multiply this by the thickness. And the thickness was what? The thickness was 10. So if you solve for the deflection, it will be 100 multiplied by 1000 squared divided by 4 multiplied by 200 times 10 to the power 3 multiplied by what? 10. So the deflection is 12.5 millimeters. That's all. So essentially, you can use either of them depending on what you have, but you still get the same results. You could have also used the other one, but still you get the same results. Let's calculate. Let's look at this question. Okay. So this one is a leaf spring, the same preamble, but then in this question, so a leaf spring is to be made of 7 steel plates. So that tells you that N is 7. The weight is 65. So B is 65 millimeters, 6.5 thickness. So T is 6.5 mm. So calculate the length of the spring, so L, so that it may carry a central load of 2.75. So W is 2.75 kilonewtons, or 2,700 and sorry 2,750 newtons. And then what else? The bending stress being limited to 160 megapascal. So sigma is 160 megapascal. Okay. So also calculate the deflection at the center. Take E. So E is 200 times 10 to the power 3 megapascal. All right. So again, the same thing. You are just making, some sort of change of subject. Nothing is new here. Okay, nothing is new here. All you have to do is to just make some change of subject, and then that's all. All right. So we want the length. So you see, there was an equation which we were using earlier on. So we will just use this equation, which has the stress and everything, and then we just solve for the length. Okay. So let me just copy this. So essentially, everything is here. So 160 is equal to 32750, and this is the length that we want. Then we divide this by 2 times the number of plates, which is 7. The B, which is the thickness, the width, the thickness is 6.5 squared. So if you solve for the length, L will become 160 times 2 times 7 times 65 times 6.5 squared, all divided by 3 times 2750. And basically, this will give you the span. So what is that? 160 multiplied by 2 times 7 times 65 times 6.5 squared, 3 multiplied by 2750. And that's what? 745.648. 745.648 millimeters. So basically, the length will be 746 millimeters. And then so essentially that's the length. So the deflection is very simple, because already we have calculated a question. We have solved a question where we were asked to find the deflection. So now that we have the stress and the length, the Young's modulus, we can just use the simple equation. The deflection is sigma L squared over 4ET. Sigma L squared over 4ET. So essentially, sigma, or the deflection, is going to be, sorry, delta, which is the deflection, 160. The length is 745.648 squared, all divided by 4, 200 times 10 to the power 3, and the thickness 6.5. Yeah. So basically, the thickness, sorry, the deflection will be 160 multiplied by 745.648 squared divided by 4 into 200 multiplied by 10 to the power 3. So you are going to get 17.10. Essentially 17.11. So essentially the deflection is going to be 17.11 millimeters, or let's say 17 millimeters. So any question up to this point? Are you following? Any question? Please. Any question up to this point? Okay. So essentially, all what you have to do is that you just have to equate some of these stuffs. Okay. And then okay. Um there are some other things which you have to know. But this is actually a leaf spring. Mostly the ones that comes in the exams is the helical spring. So maybe let me do one helical question with you. Or you can just continue. Let me use this small time to do thin word vessels. So thin word vessels is also simple. All what you have to know is the formulas. That's all. Strength of materials is all about knowing the formulas. Okay. So sorry. Okay. So let's spend some few minutes on tin word vessels. I will just give you a brief way to look at it. All right. Okay. So essentially, your tin word vessels is going to be made up of basically okay. So there is some sort of internal pressure which is built up. That's all. If you have let me give you a typical picture. So a typical example of a tin word vessel could be so it could be you know something like this. So okay, let me just so essentially a tin word vessel is actually loaded up such that there is an internal pressure built in. But then the whole idea is that there are two stresses. There is a stress which is along the axis, and there is a stress which is perpendicular to the axis. That's all. And each of them will have, you know, so we called it the circumferential and then the longitudinal stress. I just want to go through some few problems with you, and then we will just close. So let's say you have something like this, where you have been given um a cross section, a cylindrical shell, okay, and then this cylindrical shell is of 1 meter, sorry, 1.3 meter diameter, and then the thickness is what, 80 millimeters. So find the circumferential and the longitudinal stress. So as a matter of fact, questions like this is very simple. Um, the circumferential stress is always um okay. So the circumferential stress for a cylinder, we have a tin walled vessel which is a cylinder, and we have a tin walled vessel which is a sphere. Okay. So I mean, like I said, the formulas are obvious, but then always there is this thing that I want to tell you. The circumferential stress, sometimes you call them the hoop stress, is essentially one half sorry, the longitudinal stress. Okay, let's solve this question. So the formula is given by PD divided by 2T, but then if there is efficiency, then you bring the efficiency downwards. Okay. So now, basically, okay. So the circumferential stress is going to be simply the load and then the diameter divided by the pressure, internal pressure, the internal pressure. Okay, because these are actually pressure vessels. So essentially 2.4 megapascals, and then you multiply by the diameter. Okay, 2 multiplied by the thickness. That's all. But you see, this is the actual formula. But when you are given the efficiency, then you bring the efficiency downwards, which is 0.7. 0.7, which is the same as what? 70%. However, in most cases, the actual formula is PR over 2T, or P D over 2T, and it's not you just bring the efficiency if the efficiency is not 100%. Okay, and if you do this, you get what? 2.4, 1.3, 2 times 18 times 0.7, right? So essentially, what you get is actually going to be I think 1.3 times 10 to the power 3. So that the answer will be so 1.3 times 10 to the power 3. So we are getting 123.89. So let's say roughly 123.81 megapascal. However, for the longitudinal stress, so the hoop stress and the hood stress, for the longitudinal, all what you have to do, if you like, just half everything. That's all. So it's going to be PD over 4T and or the efficiency symbol. But all the time, the longitudinal stress is always going to be one half of the circumferential stress. Okay. So we have 2.4 megapascal, 1.3 times 10 to the power 3, and then 4, 18, 0.7. So essentially, this gives us what? So essentially, whatever we have here will be halved, because all right. Okay. Please. Why no? So 61.90 megapascal. So I have some few minutes left with you. I want to solve a certain question which came last year, but then it was not um, from your class, but it was a question under pressure vessels which came. So I want to solve that question with you. So I want to solve this question, and then I will close for the day. Okay. Oh, sorry. Um, I'm sorry. Let me drop the question again. This is going to be the last question I'm solving with you. Okay. So this question came last year, but it was not from your class, but it was an exam question. So it's almost time. One thing I want to do is here. One thing I want to do here is try to explain the concept, and then so we have a cylinder, and then we have been asked to calculate all sort of things here. Let's begin. So a boiler drum consists of what? Cylindrical portion, 2 meters long, 1 meter diameter, and 25 millimeters thickness. Is closed by a hemispherical end. In a hydrostatic test to 10 Newton per millimeter squared. Okay. How much additional water will be pumped in after initial filling at atmospheric pressure? Assume the circumferential strain at the junction of cylinder hemisphere is the same for both the drum material. So think about this. You have something like this, and then you have another one here, and then let's say that this is like a cylinder, and then you want to close it with what? Hemispheres. Okay. So let's begin. First of all, let's calculate the stresses. The hoop stress and the hood stress. So the hoop stress, which is also the same as the circumferential stress, is simple. PR over T, right? So the circumferential stress is PR over T. So it's going to be the internal pressure, which was what? Initially 10 Newton per milliliter squared. So 10, and then R. So like I said, some of the textbooks use R, some use D. So that is going to be what? The radius. So if the diameter is 1000, then the radius will be 500 millimeters. You know, the diameter was 1 meter. Okay, that's why we are using 500. The thickness is 25. So PRT, or PR over T will be, so we have 10 times 500 divided by 25, and that gives us 200 Newton per millimeter square. Then let's calculate the longitudinal stress, which is the same as the okay, let me put it that way. The longitudinal stress, it is going to be always 1/2 of the so the longitudinal stress is always 1/2 of the circumferential. So essentially 1/2 of 200, which is going to be 100 Newton per meter squared. Newton per millimeter squared. So after that, let's calculate the hoop strain, and then let's calculate the hood strain. I mean, so EH, or the circumferential strain, is given by 1 over E into bracket sigma h minus the Poisson ratio sigma L. Okay. So this is the formula to calculate the strain along the circumference. So it's going to be 1 over E is what? 207,000. Or let's make everything in terms of E so that the hoop stress or the circumferential stress is 200 minus Poisson ratio, which was given as 0.3 multiplied by 100. Okay. So if you do everything here, you end up with the hoop stress or the longitudinal strain as what? 170 divided by E. All these are formulas. And then epsilon L, which is the strain along the longitudinal axis, is going to be again 1 over E into bracket sigma L, which is the longitudinal stress, minus Poisson ratio into the hoop stress. So I'll get 1 over E into bracket 100, which is for the longitudinal 0.3 multiplied by sigma H. And sigma H was what? The hoop stress, which was what? 200, right? So if you do everything, you end up with what? 140 over E. Because of time, I will not go through the calculation. Sorry, it's 40. So this question came last year, like I said, but not from your class. So let's calculate the total change in volume. So the total change in volume is what? 2 multiplied by the strain along the circumferential direction plus the strain along the longitudinal axis multiplied by the original volume. Okay? And we have already solved for the strains. So we just have to put everything here. So 2 times 170 over E plus 40 over E multiplied by the actual volume, which is V. But the actual volume we know because it is a cylinder, and the volume of a cylinder is base area times height. So the volume of a cylinder is going to be pi d squared over 4 times height or the length. So the volume is going to be pi. The diameter is 1000 squared over 4, and the length is 2 meters, so it's like 2000. Now the volume is going to be 1.57 times 10 to the power 9 millimeters cube. All right. But then we have to calculate the. So this is what we are trying to do. Essentially, we have to calculate the total volume of water that must be added. But think about it this way. We have sorry. So think about this in this way. We have 1, 2, 3. So if you want to calculate for the water which we must add, then you need to consider these 3. Okay. All right. So